When you're focusing on something very close to us like this Batman, things which are far away from us like this tree gets blurred. Similarly, if you were to focus on the tree, then Batman gets blurred. Why does this happen? Well, the short answer is because our eye keeps changing its focal length. Well, in this video, we're going to explore exactly what it means, why, and how it does that. To understand this logically, we'll first take a look at a human eye. Now, an eye is a really complicated thing with a lot of parts in it, but we're going to ignore almost all of them and only concentrate on the ones which are relevant to us. And one of them is this lens. It's a convex lens that converges the incoming beam of light. And the second important part is the retina. The retina is like a screen which has all light sensitive cells. And here's the key thing. If you want to see something clearly, if you want to focus on something very clearly, then the rays of light from that object have to be focused on the retina. So I repeat, to see something very clearly, the rays of light have to be focused on the retina. So let's go ahead and draw a principal axis. And let's see what happens when we are looking at that tree which is far away. Suppose we took a point on this tree and drew a couple of rays of light coming towards our eye. Since this tree is really far away, the rays of light that are coming towards our eye are almost parallel to the principal axis. Here they are. Let's see what happens to them after refraction. Well, if you look at this ray, it is passing through the optic center, and the ray of light passing through the optic center goes undeviated. Means this ray will go and hit our retina at this point. What happens to this ray of light? Well, this ray of light will bend downwards because it's a convex lens. It will converge the beam of light. And in order for us to see this tree clearly, if we are focusing on this tree, then this ray of light must meet up with this ray at the retina. They have to get focused at the retina. So our eyes will bend these rays somewhat like this. All right? This means that the principal focus of our eyes must be at this point. Does that make sense? Because any parallel ray of light after refraction through a thin convex lens passes through the principal focus. And so this has to be the principal focus of our eye. So right now, that is the principal focus of our eye, and this is the focal length. This distance is the focal length. Now let's see what happens to Batman. All right, remember, Batman is really close to us. This distance is not to scale. That tree is far away. And also remember that our eyes are right now still focusing on that tree. So the principal focus is right over here. So let's draw a couple of rays from Batman and see where those rays of light get focused. Again, one ray of light passing through the optic center goes undeviated. And the ray of light which is parallel to the principal axis, well, that will just bend like before, passing through the principal focus. And here is our principal focus. So this ray of light will hit the retina over here, and as a result, can you see the two rays of light are not being focused on our retina? They might get focused somewhere behind the retina. And that's the reason, and as a result, Batman will not get focused right now. And that's exactly what's happening right now. The rays of light from this tree, which are almost parallel to each other, the green rays of light are being focused onto our retina, but the rays of light from that Batman is not being focused, so Batman is blurred. So this is the case when we are looking at things which are far away, when we are focusing on things which are at large distances. Okay, now let's say you want to focus on Batman. What should your eyes do? Again, if we just look at the ray diagrams, we can figure this out. Now, if you want to focus on Batman, that means these rays of light must meet on the retina. Well, this ray of light will always go undeviated, so nothing can be done over here, which means that our eyes must bend this ray, all the way to meet here. And that can only happen if this were the principal focus. So in other words, when you are focusing on Batman or something which is very close to you, the principal focus comes closer. The focal length of your eye gets shorter. So this is now the new focal length. And now what happens to the rays of light from tree? Well, I'm pretty sure you can guess now. The rays of light from the tree are parallel. Again, this ray goes undeviated. It doesn't matter what the focal length is. But now this ray of light, well, it has to pass through the focal length. And so it'll also bend the same way. And as a result, now the rays of light from the tree are no longer focused on the retina. They're now being focused over here. And that's why when you focus on Batman, the tree gets blurred. And this is the situation when you're focusing on things close to us at short distances. So the key takeaway is that when your eyes are focusing on something at short distances, very close to you, they require short focal length. And while focusing on something at large distances, they require large focal length. And it is for this reason, when you're focusing on one object, the other one gets blurred. So we have pretty much answered our question, but let's go a little bit deeper. Well, first of all, this ability that our eyes possess to change its focal length, it's given a name. It's called accommodation. Accommodation. So accommodation is the ability that our eyes have to change its focal length depending upon what it's focusing on. Well, the big question is, how does our eye decrease its focal length? What does it do? Well, think about it. If you want to decrease the focal length, then the rays of light must bend more. Does that make sense? And what does this bending depend on? Well, the bending really depends on the curvature of our lens. More the curvature of the lens, more will be the bending. So in order to decrease the focal length from here to here, the lens must be more curved. And how does that happen? Well, this is not a glass lens. Obviously, we don't have a piece of glass in our eyes. This is a lens which has some fluid inside it, and so its shape can be easily changed. So our eyes do that. They make this lens more curved by just pushing on it from the top. So when it gets pushed, it gets squashed a little bit, and as a result, it ends up getting bulged. So something like this happens. See here. So it'll get bulged a little bit, and as a result, the lens is now more curved than before. Of course, I've exaggerated over here, and that's how the focal length decreases. And similarly, if you want to increase back the focal length, bring it back to what we had before, well, then you let go of this pushing force, it'll snap back over here. So this is how accommodation happens. But then we can further go ahead and ask, well, what's making that? What's pushing this lens? Well, there are a couple of muscles over here which I haven't shown. Let me show that. It's these muscles called the ciliary muscles. The name is not so important, but they are the ones which are responsible for pushing on this lens and decreasing its focal length. And again, if they release that pushing force, the lens snaps back to its normal position, and now the focal length increases. Of course, in reality, it's a little bit more complicated than that, but we don't have to worry too much about this. So as the objects come closer and closer, the ciliary muscles start pushing onto it to make that lens more curved so that the focal length decreases in order to see the object. All right, one last thing is that if our Batman were to come even closer, then if you drew the same ray diagram again, the focal length should get even shorter. Closer the distance, shorter the distance of the object, shorter is the focal length. And that means our lens must get even more curved. But there is a limit to how much your lens can curve, and therefore there's a limit to how short the focal length can be. Suppose now we have reached the limit. Then this is the nearest distance at which you can keep an object and you can still focus it. And that point we usually represent as D, and we call that as the near point. So near point represents the shortest distance at which you can keep the object and still focus it. And now if you kept the object, if Batman were to come even closer, well, now the ciliary muscles can't push anymore. We have reached our limit, and so we cannot shorten the focal length anymore. And as a result, this ray of light cannot be focused on the retina anymore. It can't, because it needs to have a smaller focal length. And so as a result, the focal length will not get shortened anymore, and so the rays of light will no longer get focused. And you can test this. Just take your finger and bring it very close to your eye, and you will see you will not be able to focus it. The near point distance really depends on a lot of factors, but the average distance, we usually take that as 25 centimeters. This means any object kept closer than 25 centimeters cannot be focused on our retina. Remember, this is an average distance. It doesn't mean every eye has a near point of 25 centimeters. Some eyes will have smaller than that. Some eyes will also have larger than that. Interestingly, our eyes don't have a far point. There is no limit to how far an object should be to bring it to focus. Even if the object was at infinity, for example, stars at large distances, you can still bring them to focus. This is the maximum focal length that our eyes have, and so those rays can be easily focused over here. It's only the minimum distance that matters to us. That's the near point that matters to us. So to quickly summarize everything, our eyes adjust its focal length depending upon how close or how far the objects are to bring them to focus, and this phenomenon is called as accommodation.